Introduction to long-term monitoring of the internal atmospheric environment. So why long-term atmospheric moisture monitoring? Well, indoor and outdoor atmospheric moisture can change rapidly over short periods of time. Outdoor atmospheric moisture levels influence indoor levels. Long-term monitoring records these changes better than a simple measurement during an inspection, allows long-term review of conditions within a property in relation to heat, moisture production and ventilation. Long-term monitoring can be especially useful in landlord and tenant disputes in relation to dampness in buildings. It will identify what one could refer to as a potentially long-term damp environment. So let's have a look then at relative humidity and vapour pressure, both very important in long-term atmospheric monitoring. Relative humidity is a measure of saturation. It relates to how much water is retained in the air as a proportion of the maximum that could be retained at the same temperature. For example, 70% relative humidity shows that the air is retaining 70% of the maximum that it could possibly retain at that temperature. Remember, it is a measure of saturation. Vapour pressure, on the other hand, water vapour exerts a pressure. The greater the amount of water vapour, the greater the vapour pressure. Therefore, it is effectively a measure of the amount. And continuing with relative humidity and vapour pressure, here we have relative humidity, as we mentioned earlier, is a proportion. And note that relative humidity is temperature related. So if we imagine the air as a bucket, the warmer the air, the bigger the bucket, and therefore potentially more water vapour it can retain. Similarly, colder the air, the smaller the bucket. And we can see that in this diagram. If we took the top level of moisture, that in the green at 20 degrees, and put it in the bottom bucket at 10 degrees, then clearly our relative humidity would come to about 100%. In other words, the air would be fully saturated. In relation to vapour pressure, this simply reflects the amount of water vapour in the air. And note, unlike relative humidity, vapour pressure is not temperature related. We could double the size of the bucket, say at 20 degrees, treble it, quadruple it, but we would still have the same amount of water vapour in it. It would not make any difference. If we look at UK external atmospheric conditions, the vapour pressures, note there is less water vapour in the air during the colder months of the year. In the warmer months in the summer, there's a lot more. So where do we go with our long-term monitoring? Well, we can use data loggers, and this is just an example. These record temperature, humidity and dew point temperatures, and we can do this at set intervals, for example, setting them to record every 30 minutes. So the data recorded from a data logger, basically it's in text form, as we can see on the left: date, time, temperature, relative humidity and dew point. The software that comes with the loggers will also produce a graph showing temperature, relative humidity and dew point. So where do we place the data loggers? This is quite important. Well, if we look indoors, keep away from heat sources, keep away from windows, try to keep over 15 centimetres away from a wall surface, and place where the airflow is not restricted. Outdoors, try to keep away from direct access to elements and position to allow a good typical airflow. How long should the monitoring period be? Ideally as long as possible. 4 weeks is a reasonable period. 2 weeks should be considered minimum. Interval between readings, well, about every 30 minutes. That would give us 48 readings per day. But it is important to keep these things out of reach of children and animals, and anywhere they are likely to be interfered with. Do not move them when in use. If you do, then tell the investigator. We can use them to assess long-term relative humidity indoors. And here's an example, quite nice, relative humidity running between 40 and 50%, temperature around about 20 on average. Another example, here we can see that the relative humidity is in excess of 80%. This means there is a mould risk to susceptible items within the room, anything really greater than 75%. Note it was, however, quite cold. Once we've got our data, we can manipulate it. The text data can be exported to Excel as a CSV file, and these can be converted to vapor pressure and indeed relative humidity at a constant temperature, as we'll see later. Note that vapor pressure is directly proportional to the levels of moisture in the air. The external vapor pressures are related to external temperatures, and if we look at it, that's simply less water vapor in the air during the colder months. So what is the influence of external vapor pressure on internal vapor pressure? Very important. Here's the graph showing an example, external vapor pressure in red, internal vapor pressure in blue. Note, as the external vapor pressure drops, so will the internal levels. We can also undertake more manipulation of recorded data. Remember, vapor pressure is directly proportional to the levels of moisture in the air, both indoors and outdoors. And vapor pressures can be used to produce what is known as differential vapor pressure or excess vapor pressure. That is the difference between internal and external atmospheric moisture. And this will give us the internally generated water only. It will exclude the external levels, which of course influence internal levels. And we can see that in this diagram. On a warm winter's day, the total moisture was internally generated moisture and quite a lot of external generated moisture. Whereas on a cold day, when the external levels drop, we can see that the overall moisture level drops, although the internal moisture level could remain the same. Thus, the differential vapor pressure leaves internally generated water only, and this is basically what we're interested in. The external water vapor levels can therefore have a significant influence on the overall internal levels, as we saw previously. But note, moisture from damp walls and floors is unlikely to contribute any significance to internal atmospheric moisture levels, and I exclude flooding in this. So then, to recap where we've got so far, differential vapor pressure reflects internal moisture production, and indeed ventilation. That is, it reflects the overall amounts of internal atmospheric moisture. Relative humidity is a reflection of saturation of atmospheric moisture. It's as a proportion. And, don't forget, it's temperature related. For example, low amounts of atmospheric moisture under cold conditions will result in high relative humidities. The same levels, however, under warmer conditions will result in lower levels of relative humidities. High relative humidities, remember, increase the risk of mould and other organisms. If we want to look at a property, we have monitored properties with no known damp problems, and we've found that these contain a differential vapor pressure of up to an average of around 0.45 to 0.5 kilopascals. And this may be regarded as acceptable during the colder months of the year, but other factors may need to be considered. However, it is a very useful guide, the 0.45 and 0.5 kilopascals. Differential vapour pressure during the summer, it just shows the effect of good ventilation. One can see the mean is at the 0 point on the left. There is as much water on average internally as there was externally, but do note the massive variations, all shown in blue, throughout the year. But when we come to the colder months of the year, we can see that we have more water vapour internally. In other words, the differential vapour pressure is increasing. Why? Well, basically, we are now closing the windows, we are slowing down the ventilation, and the internal atmospheric moisture is starting to build up. This is an internal investigation in a London flat in the summer of 2014. Now, I hasten to add, don't really do anything in relation to internal atmospheric moisture monitoring during the summer. However, there was a lot of hassle over this particular case, and in essence, there was a force to get somebody in there to look at it, and this was a result. Even in the summer, the internal, or rather the differential vapour pressure was high, varying between about 0.6 and 0.4 kilopascals differential. Expected ventilation in a well-averaged property, probably around about 0.2, possibly a bit more, but this was much, much higher. But in the winter, I'm sure it would have been a much greater problem. Long-term monitoring again. What do we have here? Notice the big dips. These dips in the differential vapour pressure occurred when the property was unoccupied. And it shows up quite clearly in many of the monitoring situations. The problem was only occurring when the property was occupied. Another one, it was reported unoccupied for a period, and it shows when it was occupied, we had the differential vapour pressure getting up towards 0.7 to 0.8 kilopascals. When it was unoccupied, it was around about 0.1 to 0.2. The maximum average expected in non-problem properties, as we mentioned earlier, is about 0.5. Temperatures and relative humidities again in a different flat. These were the basic results with temperature and relative humidity. Got quite high humidities going over 75 towards the end of the monitoring period. The temperatures varied, but we had this wavy yo-yo-like appearance of temperatures somewhere during the monitoring period. So what was going on? Well, when these were converted to differential vapour pressure, we could see what was happening. The yo-yo appearance of the temperatures, although it didn't show up too much on the relative humidities, clearly now showed up when the flat was occupied versus unoccupied. Moisture in solid floors and walls can also be measured, and can use it with a little box or the data logger under polythene put on the floor with a data logger on top. Any water vapour escaping into a confined space will give us the vapour pressure, and that can be compared to the vapour pressure in the room. If that from the floor is much higher, then the floor is damp. However, with internal conditions, it's effectively relative humidity that is a major factor. Why? Because it's the relative humidity that potentially leads to health problems. That is what we would call a damp environment. Relative humidities can change rapidly due to many factors, including changes in the external environment. Hence the importance of long-term monitoring. So, looking at the importance of relative humidity, fundamentally, or the most common, is mould growth. That is what we can see. And moulds can develop on certain moisture-sensitive materials by maintenance of relative humidities in excess of 75%. Wood, leather and cardboard, but especially leather, are notorious. Surface temperatures of walls, especially external facing and where airflow is restricted, are inevitably several degrees lower than the room temperature. This simply means that the boundary layer of air, that is, the air in contact with such cold surfaces, is cooled, and therefore the relative humidity will increase. It will be therefore in excess of 5 to 15% greater, sometimes even greater than that, and certainly greater than that in the room. And these conditions will then lead to a risk of mould growth occurring in such situations. In addition, a cold environment will almost certainly lead to higher relative humidities under what we could regard as normal airborne water levels. So, raising the temperature lowers the relative humidity and reduces the risk of mould and dust mite development. And we can see that in the diagram. Here's a room, it's 14 degrees, 80% RH, and of course 80% RH, there's a risk of mould. If we increase the temperature in the room to 20 degrees, then this will drop the relative humidity to around 50%, and the risk of mould declines to effectively zero risk. Further examination showed that we could use living areas for our examinations. In living areas during the colder months, up to around 60% relative humidity at 20 degrees, and this should be an average, should be achievable. A practical method of making assessments is to make an assumption, and that is to assume the internal occupied levels are a constant 20 degrees. If after that assumption the relative humidity is, again on average, it's got to be the average, much above 60%, then ventilation is needed. If after that assumption, on average, it drops below 60% relative humidity, then an increase in heating is required. However, this can only be assessed over a period of time. A single snapshot of conditions is unlikely to reflect the average condition. Interesting case. This was a property where the actual temperatures were quite low, between 12 and 18. The property had what we could loosely call a damp problem, but again, as mentioned just now, it was cold. And even heating to 20 degrees, the relative humidity still remained high. That's on our assumption, of course, of our 20 degrees being the result of heating. We can see here the relative humidities in the diagram, and they're still pretty high and just occasionally hit the mould risk. So basically, more ventilation is needed to reduce the relative humidity. However, it is interesting to note that at the end of November onwards, our relative humidity dropped dramatically. So why was this? It was simply due to external moisture levels dropping. Remember, the external levels of moisture influence the levels of moisture internally, and it dropped quite dramatically simply because it was so cold for that long period externally. Another problem that occurred, a kitchen with mould in the cupboards. And note the very high relative humidity in the cupboard where there is mould. It was over 90%. It was in a kitchen. However, if we then did our conversion and made the assumption that the cupboard was now 20 degrees, and then compared it with the assumption that the kitchen was at 20 degrees, we can see that the data was very, very similar. Thus the high relative humidity in the cupboard was solely due to the very low temperatures. And we can also compare the kitchen and the cupboard vapour pressures. And we can see here, by looking at the amount of water vapour in the cupboard and the amount of water vapour in the kitchen, they're virtually identical. So the cupboard was a ventilation problem, effectively. It was just cold in there. It was thought that the walls were damp and they were adding to the environment in the cupboard, but that was not the case. So the vapour pressures are very similar in both areas. There was no excess water in the cupboard. However, it is very important to appreciate that surface temperatures of walls and other cold areas will inevitably be several degrees lower than the room temperature. The relative humidity in the boundary layer of air against such surfaces will therefore be in excess of 5 to 15% higher, and in some cases we've measured as much as 25%. And of course this will result in a much greater risk of condensation and mould growth. Surface temperatures are therefore important, especially in the long term. And here's some examples of surface temperatures and the differences between internal air and those surfaces. Obviously assorted properties. The main thing to note is the difference, especially between the base of the wall and the internal air. And of course this coldness, or colder than the internal air, leads to higher relative humidities in the boundary air at the wall surface, and therefore a greater risk of condensation and mould. Note in the figures, some areas have a difference between the base of the wall and the air temperature, standard air temperature, of nearly 13 degrees. Some of them are very high indeed. So we have a very large difference between air temperature and surface temperatures under some circumstances. We can monitor the wall surface temperature in the long term by using data loggers, these special data loggers. They look rather like watch batteries and record temperature, and these are fixed to the wall. However, as one can see, they are very small and therefore easily swallowed. So if one is going to use these, take extreme care where there are children and pets. Possibly, depending on the conditions, don't use them. So looking at air and surface temperatures, the top graph shows constant heat. We can see the blue is the air temperature and red is the wall temperature. Note they are virtually parallel to each other. When the air temperature goes up, so does the wall temperature. So raising the room temperature will also raise the wall surface temperature. And this is especially the case when we look at intermittent heating. There's the blue and then the red as we had before for the wall temperature, and look at the effects. It's very rapid. Wall surfaces heat up very rapidly in relation to heating up the atmospheric temperatures within the room. And doing this, if we heat up the wall surfaces, this can lower the risk of mould growth. Good example here was moving some furniture. Furniture was moved and the temperature behind that furniture was about 10 degrees. The normal wall temperature was 18. However, once that furniture had been removed, the circulating air started to warm up the surface of the wall. So the surface temperatures improved shortly after removing the furniture and eventually came up to the same level as the rest of the wall. It is the air temperature that is now influencing the surface and not what we could loosely call the coldness within the wall. Again, this shows up on another practical situation. Note how the internal surfaces rapidly respond to internal air temperatures. I've put the arrows in there to show when the air temperature goes up, the surface of the wall goes up or down, but they follow each other very closely. On the other hand, if we look at external air and internal wall surfaces, the influence of external temperature on internal surface temperatures is not immediate, but it is much slower. And again, I've put the arrows in there simply to show that when the external air temperature drops, the internal wall surfaces didn't. They're far more related. The internal wall surfaces are far more related to internal air temperatures. The effects of external air on the wall or on the surface temperatures, basically on the wall, are much, much slower. And if we know the internal temperatures, RHs and dew point, and the wall surface temperature, we can compare the surface temperature with the dew point temperatures. And here's an example here. We can see in this case, where it's in the red, the wall surface was well and truly into condensation during most of the monitoring period. Intermittent condensation, and this is quite common, where it occurs not during the daytime, but in this case it was occurring during the night, or at times when people aren't there, perhaps out during the day. And this is the big advantage of long-term atmospheric monitoring. The red indicates wall surface temperature and the green atmospheric moisture. And if we look at the graph, or the principle of the graph, we start off on the left-hand side. The wall surface temperature starts rising when the occupants come back from work, put the heating on, this is winter of course, and the air temperature in the room increases, as indeed does the wall temperature. It follows it basically. And then when they go to bed, they switch off the heating and the wall surface temperature declines, and when they get up in the morning they put the heating on and it goes up again. If we look at the relationship between atmospheric moisture, then obviously when they come into the property, they start breathing and cooking, the atmospheric moisture levels go up. However, when they go to bed, the atmospheric moisture doesn't lose very rapidly from the room, but the wall surface cools right down, and we therefore can get condensation, say, during the night between 2 and 3 o'clock in the morning based on this behaviour. It's an intermittent condensation, and it can only be determined by long-term atmospheric monitoring. So, to conclude, long-term atmospheric monitoring is the key to determining and identifying indoor air quality problems, which can lead to damp environments. Such conditions will promote the risk of development of dust mites, mould, bacteria, viruses, and other factors which can affect the living environment in relation to comfort and especially potential health problems. Long-term atmospheric monitoring of the various parameters can significantly aid in identifying the specific factors causing reported problems. And finally, long-term atmospheric monitoring may be useful for landlords and tenants where issues relating to dampness and its causes arise. And that is the end of long-term monitoring of the internal atmospheric environment. Thank you very much for listening.